Slide 1. Shoreline Features, Topic 06b. Slide 2. Estuaries. Estuaries are places where the ocean is partially surrounded by land. They go by many names: bay, sound, lagoon, and more. The mouth of a river, harbors, and marinas are all examples of estuaries as well. Estuaries can form along the shoreline in several ways. When sea level was lower, rivers and glaciers, huge blocks of ice that flow down from the mountains, carved out valleys at the location of the present shoreline. When sea level rose, the ocean flooded the valleys, and they became estuaries. In other places, sand piles up offshore, becoming a barrier island, or barrier bar, which partially cuts off a body of water from the ocean. Also, earthquakes can raise the ocean floor or lower land to create an estuary. This is how the southern end of San Francisco Bay formed. The land sank. Slide 3. Ocean waves and currents are not responsible for as much of the water motion in estuaries as elsewhere along the coast, because the partially surrounding land blocks waves and currents coming from some directions. Thus, the water in estuaries tends to be calmer than elsewhere along the coast due to fewer and smaller waves. Tides play an important role in causing water motion and creating currents in many estuaries, and are often the major cause of water motion in estuaries. As sea level rises towards high tide in the ocean, water flows into the estuary, and when it sinks toward low tide, water flows out of the estuary. The water flows downhill, pulled by gravity to even out the surface of the ocean. In estuaries that are large and have narrow or shallow connections with the ocean, it can take a long time for the water to flow in or out. The greater the size of the estuary and the smaller connection with the ocean, the faster the water flows into or out of the estuary. Tidal currents can be quite treacherous and can be an important factor in causing mixing in an estuary. Slide 4. The value of estuaries. Ocean life is especially abundant in most estuaries. Most estuaries get a lot of fresh water runoff from the surrounding land, particularly if a river flows into them. Since rainwater comes in from two or more sides, estuaries get more runoff than other places along the coast. The fresh water itself is bad for most ocean animals and algae, but most estuary animals and algae have adaptations that help them survive in the not very salty water of estuaries. The real benefit of the fresh water runoff is that it carries nutrients from the soil on land into the ocean. Because land wraps around the water of the estuary gets extra runoff and thus extra nutrients, since there is more land nearby, compared to most places along the coast. In addition, the nutrients that go into the estuary tend to be trapped. They stay in the estuary longer than nutrients washed into the ocean elsewhere along the coast. The nutrients in estuaries do not drift out to sea as easily as nutrients along the open coast, because the land blocks waves and currents coming from some directions, preventing the waves and currents from taking the nutrients away, and there is only one way to exit instead of several directions to go in. The abundant nutrients lead to the growth of lots of algae, both macroalgae, seaweeds, and phytoplankton. The algae are food for animals. Estuaries are often called nurseries for ocean animals, because many ocean animals go to estuaries to breed or lay their eggs. Recall that most ocean animals do not take care of their babies. See Unit 2A1. The eggs hatch and in most species become zooplankton who feed on phytoplankton. The juvenile, baby, animals can find lots of food, like phytoplankton, in estuaries. In addition, estuaries provide hiding places, like among the seaweed, in nearby wetlands, and in the mud on the bottom of the estuary. Also, many large ocean predators do not like shallow water, because they are afraid of getting stuck at low tide. Some ocean predators are not well adapted to tolerate a mix of fresh and salt water. Juveniles of many species are adapted to tolerate the low salinity, less salty, water of estuaries, but lose the ability as adults. When they get older, they leave the estuary and swim off into the ocean. Estuaries are valuable to people because they provide food. We eat both animals who live in estuaries and animals who live in the ocean but grew up in estuaries. In addition, estuaries are important for trade. Calmer water makes it much easier and safer to load and unload cargo, and do maintenance and repairs on ships. For example, over $200 billion in goods pass through the ports of Los Angeles and Long Beach each year, and such trade is linked to over 800,000 local jobs worth $39 billion in wages. These ports are the busiest in the United States, 8th busiest in the world. Over 40% of all the goods that we import come through these ports. Given their economic value, you won't be surprised to learn that throughout history people have built estuaries along coasts without good ones for ports or in places where a port is needed. An estuary is created by building wall in the water to mostly cut off a body of water from the rest of the ocean. The wall is called a breakwater. See Unit 6A for more information about structures that people build along a coast and why they build them. Estuaries are also valued for recreation, like sailing and swimming, and by some industries, like fish farming, where people prefer calmer water. Estuaries can be loved to death by humans, who often pollute them both intentionally, through sewage pipes and industrial chemicals, for example, and unintentionally, like storm drain runoff and toxic chemicals leaking from boat paint. Earlier we learned that it is hard for nutrients to drift out of estuaries into the ocean. The same goes for air pollution. Thus, estuaries are often more polluted than the nearby ocean, since it is hard for pollutants to leave, to drift out and spread away. Slide 5. Wetlands. Wetlands are marshy or swampy areas that are out of the water part of the time and covered by water part of the time, hence the name wetlands. In coastal areas, wetlands are covered by water about half the time at high tide, though freshwater runoff can play a role as well when it rains. Wetlands are often found along the borders, edges, of estuaries. There are two kinds of coastal wetlands, salt marshes and mangrove forests. Both are covered by special, salt water-tolerant plants. Not ocean algae. Salt marshes are dominated by grasses, reeds, while mangrove forests have mangrove trees. Some plants have thick outer layers to keep salt water from getting into them and fresh water from leaking out. Other plants excrete salt crystals, letting rain wash them away, or concentrate the salts in their leaves and drop the leaves to keep the salt from getting back into their bodies. In addition, these plants have to be able to survive in low oxygen conditions. This may seem strange, given that plants can make oxygen, but plants do not make oxygen at night. Like us, plants need the oxygen to burn the food that they made during the day, to break down carbohydrates and power their bodies, a process called cellular respiration. Plants can extract oxygen using their roots, but wetland plants' roots are buried in thick mud with little oxygen in it. The oxygen in water cannot penetrate through the thick mud. There is no space or room for it. Some plants have wild root systems, the most famous being those of mangroves, that actually stick out of the waters so that the plant can get oxygen, can breathe. The lack of oxygen in the mud is related to the stinky smell of some wetlands. The smell is sulfur in gases given off by special bacteria living in the mud who can survive without oxygen. In fact, oxygen is bad for them, which is why they like the mud. Slide 6. Life in wetlands. Like estuaries, life is especially abundant in wetlands. In fact, more photosynthesis takes place per square foot in wetlands than in any other ocean environment. In other words, more food is made in wetlands than anywhere else in the ocean. This is what scientists mean when they say that wetlands are the most productive places in the ocean. Like estuaries, there is more photosynthesis happening, because there are more nutrients in the water. Wetland plants get in the way of rainwater runoff, slowing it down, and thus give themselves and algae-like phytoplankton more time to absorb the nutrients. As you might imagine, wetland plants and algae are good at absorbing as many nutrients as they can before the runoff flows into the ocean. Ironically, very few animals actually eat the living plants in wetlands, presumably because of the thick outer layers that keep out salt and keep in the water. Most animals at the bottom of the food chain eat phytoplankton or wait for the plants to die, and then eat the dead plant matter after it has been partially decomposed by bacteria or eat the bacteria. Like estuaries, wetlands also serve as nurseries for ocean animals, providing food and hiding places, like in the small spaces between the plants. Many animals hide beneath the mud of the wetlands or the neighboring mudflats, places where the muddy bottom of the estuaries is exposed during low tides. Some animals, like worms, devour dead material that has fallen into the mud. This is called deposit feeding. Others burrow up to the surface when water covers the mudflat and strain phytoplankton and zooplankton out of the water. This is called suspension or filter feeding. Birds in particular love wetlands for the abundant food in the water and mud, and protection from land predators which cannot swim, like cats. Slide 7. The value of wetlands. Wetlands are an important food resource for the same reasons as estuaries. See the previous slides and audio discussion. Remember, many ocean animals need wetlands to reproduce effectively, even if they do not live there most of the time. Perhaps the most important difference between estuaries and wetlands is the presence of plants. The wetland plants get in the way of rainwater runoff flowing off the land into the ocean, slowing it down. This allows small sediments, mud, to settle and build up new land by the coast. In addition, the roots of wetland plants hold onto the sediments, both helping to build up new land and reducing coastal erosion by waves. Wetland plants and mud are good at absorbing water, like a sponge, keeping heavy rains and storm surge, sea level rising during storms, from flooding our homes and businesses. In addition, wetland plants get in the way of floods and storm surge, slowing them down. If the plants slow storm surge down enough, the storm may move up the coast and take its storm surge with it before the storm surge gets through the wetlands to our coastal cities. In short, wetlands protect our homes and communities from floods, including water flooding in from the ocean like storm surge. The slowing of the water gives water more time to soak into the ground. Thus, wetlands increase our underground supplies of fresh water, groundwater, in aquifers, bodies of rock that hold water. It is important to keep coastal aquifers filled with water. If we take out too much water, and water is not soaking in from above, ocean water will come in from the side to fill in the empty space in the rock, poisoning the aquifers permanently. If this happens, people who live near the coast will lose an important supply of fresh water. Wetland plants absorb excess nutrients in fresh water runoff from fertilizers and untreated sewage, keeping them from entering the ocean where they can lead to the growth of toxic algae, like some red tides, or dead zones, a place in the ocean with little or no oxygen in the water. All algae need nutrients for photosynthesis, and like some plants on land, some species of algae make chemicals that are toxic to us. Freshwater algae can make water very dangerous to drink or even touch. Ocean algae only poison our food supply. There are exceptions. Dead zones result when too many nutrients enter the ocean, because the nutrients encourage the growth of an enormous number of phytoplankton, who need the nutrients for photosynthesis. Most bacteria use oxygen to decompose dead material, and bacteria end up removing most or all of the oxygen from the water. Animals suffocate, cannot breathe, and must leave the safety of their homes or die. Recall that many animals are more or less stuck in place and cannot leave. Nutrients, dissolved metals, and toxic chemicals like pesticides in rainwater runoff get buried in the sediments, mud, as the sediments sink and build up when the water slows, trapping the pollutants in the sediments. It is far better for these chemicals to be in the wetland sediments than in ocean water, where they are far more likely to get into the food chain. In addition, some toxic chemicals biodegrade faster in the low-oxygen soils of wetlands. Some species of oxygen-hating bacteria can break the chemicals down. Because of the abundance of plankton to eat, lots of filter feeders are present in wetlands. Some superfilter feeders like clams and sponges can remove extraordinarily tiny bacteria and viruses from water in addition to plankton, including bacteria and viruses that make ocean life, humans, and other land animals sick. The wetland plants get in the way of rainwater runoff from the land, slowing it down, giving sunlight, salt water, sinking sediments, and wetland organisms more time to kill or trap harmful bacteria and viruses from the land before they get into the ocean. Thus, wetlands serve as important filters, keeping pollutants from entering the ocean. In short, wetlands clean runoff from the land, and thus help make the ocean cleaner as well. In fact, some cities have built wetlands to serve as treatment facilities for wastewater. In some cases, cities have done so after destroying their natural wetlands and finding that their local water became dirtier as a result. Man-made wetlands have a mixed track record and most are not as beneficial as natural wetlands. We have destroyed about 50% of our wetlands in the United States. The Los Angeles area once had extensive wetlands. For example, the entire area of the ports of Los Angeles and Long Beach used to be covered by wetlands. These wetlands extended all the way to the Madrona Marsh by the Del Amo Mall. Imagine! There was a time when you could paddle a canoe all the way from San Pedro to Torrance. In California, only 10% of our wetlands remain. Developers can still destroy wetlands in California, but the laws of the state now make them perform a mitigation project to reduce the damage. They must build a man-made wetland or help extend a natural one to compensate for the wetland that they destroyed. Slide 8. Deltas. A delta develops when sediments pile up at the end of a river. Sediments will pile up if waves are unable to carry all of the sediments away down the coast, longshore transport of the sediments. Tidal currents and river currents can also help push sediments out of the way. Big deltas typically form at the ends of rivers, because big rivers tend to carry a lot of sediments. Big rivers carry more water, and more water can push more sediments down to the coast. Deltas also form at ends of rivers where waves are small and heading towards the delta instead of approaching the coast at an angle. Small waves are weaker and push fewer sediments down the coast and away from the mouth of the river. If more sediments come down the river than are taken away by waves, sediments will pile up at the end of the river. A delta will form. Waves can only push sediments down the coast, cause longshore transport, if they approach the coast at an angle. If waves head directly towards a delta, they push sediments back into the mouth of the river and actually help the sediments build up in the mouth of the river. As more and more sediments pile up, they block the end of the river, causing it to split into smaller rivers called distributaries. The distributaries spread out, each finding its own way through the sediments and down into the sea, sometimes giving the delta a triangular shape. The Greek letter delta has the shape of a triangle. When sediments clog the end of one distributary, a new one starts. If enough sediments block the river itself can actually shift its course. Slide 9. One famous example of a delta is the Nile Delta in Egypt. When you think of Egypt, you probably think of pyramids and a barren place covered by sand, but the delta is a green place with lush vegetation thanks to all the nutrients in the river water. When a distributary or river shifts, it can cause flooding, but where it once flowed it leaves behind nutrient-filled sediments that are great for growing crops, for farming. Many great ancient civilizations started in deltas because of the rich farmland. Think of Egypt, Mesopotamia, China, and India, just to name a few. Slide 10. Many people still live in deltas, but unlike ancient peoples, we have the technology to keep the delta from changing. For example, we remove sediments from the bottom of the river and distributaries, we dredge them, to make it safe for ships to travel without running into the bottom, and build levees, big piles of sediment, to keep our homes and businesses from being flooded by the river or distributaries. In California, we have a delta at the north end of San Francisco Bay, the Sacramento-San Joaquin Delta. Levees broke there in June 2004, flooding people's homes and fields. Governor Schwarzenegger asked for federal emergency relief funds, rather than using California's tax dollars, to help shore up the delta's levees, an interesting strategy since typically these funds are used to clean up after a natural disaster, not prevent one. It would certainly cost less to prevent the problem than to clean it up. Natural deltas are places where land is growing along a shoreline, because new sediments are continually brought by the river and its distributaries. If the river is dredged and controlled by man-made levees so that it cannot change course periodically and dump sediments all along the coast, then most of the sediments never reach the coast or are funneled out into the ocean. Slide 11. Waves are constantly eating away a delta, carrying sediments away. If fewer sediment are piling up in the delta, waves may begin to take away more sediments than are accumulating in the delta. In other words, waves to begin to erode the land of the delta. In addition, the land of a delta sinks over time. Water in the deeper sediments is slowly squeezed out by the weight of the sediments above, and the sediments above sink down and fill in the space previously occupied by the water. A good example of land sinking in a delta is the city of New Orleans, which is located in the Mississippi Delta. New Orleans is now about 8 feet below sea level, on average. In places, it is over 20 feet below sea level. The levees are the only thing keeping the river and the ocean out. Slide 12. Barrier islands. Barrier islands are long, thin piles of sand that run along the coast. In other words, barrier islands are long, thin, sandy islands that are roughly parallel to the shoreline. The water trapped between the island and the coast is an estuary, called a lagoon, and wetlands grow along its edges. The side facing the ocean endures the pounding of ocean waves, thus protecting the mainland from wave erosion and flooding by storm surge, the rise in sea level caused by storms. Slide 13. Because barrier islands are essentially large piles of sand, they shift as waves push sand from one place to another. In addition, large storm waves smashing into the islands can push barrier islands back, toward the land. This is called barrier island migration and has been well documented. Slide 14. Barrier islands are common along the eastern and southern, Gulf, coasts of the United States, presumably due to their shallower, flatter continental shelves, making it easier for piled-up sand to reach the surface, and because more sediments were left over from previous ice ages. Lots of sand is necessary to create an island made of sand. When sea levels were lower, the continental shelves were flat plains on land. As sea level slowly fell and then rose again, every spot on the continental shelf was part of an ancient shoreline for a time. Rivers brought sediments, and waves spread sand out along these shorelines. The sand was left there when sea level rose and flooded them, and the sand of these ancient beaches became part of the ocean on continental shelves. Several processes have been suggested to explain the origin of barrier islands. One is that they form like a summertime beach. Sand from the ocean floor is pushed towards land by waves and piles up. This has been observed. Another is that rising sea level flooded the coast, leaving only the highest dunes of the original shoreline's beach above water. Not seen yet, but sea level has not risen that much. The last suggestion is that a beach literally leaves the coast at a bend in the coastline. This has actually been observed, but does not explain the origin of most barrier islands. Slide 15. Headlands and coves. Headlands are places where the land extends out into the ocean, small peninsulas. Coves are the places between headlands, where the ocean pushes into the land. Slide 16. When waves erode a shoreline, they encounter some rocks that are more resistant to wave erosion than others. The places where the rock is less resistant, softer, erode faster and get pushed back faster and become coves. The wave-resistant rock is left sticking out into the ocean when the less resistant rock on either side is taken away. The leftover wave-resistant rock is the headland. Sooner or later the wave-resistant rock will completely erode away. It just erodes slower than the less resistant rock. Along the coast of California, igneous rock, cooled lava, tends to resist erosion better than sedimentary rock, rock made of stuck-together sediments. Slide 17. Sea arches and sea stacks. Often a small amount of wave-resistant, harder, rock protects softer rock behind it. As the shoreline on either side retreats more and more, the waves begin to refract, change direction and turn towards the coast, attacking the softer rock behind the end of the headland and eroding it. Eventually, the wave-resistant rock is left standing alone. It has become a sea stack. Sometimes the waves erode all the way through the less resistant rock behind the end of the headland, but the end of the headland and the mainland support the rock above. This feature is called a sea arch. The space beneath the arch continues to widen until the rock on either side cannot support the weight of the arch and the arch collapses. The fallen rock is made of the less resistant rock, so it is ground up into sediments by the waves and carried away. All that remains is the sea stack, the wave-resistant rock. Slide 18. Wave-cut terraces and marine terraces. When waves erode a shoreline, they push back the cliffs, leaving behind a broad, flat area called a wave-cut terrace, also known as a wave-cut bench or platform. The waves push forward, not down. Waves cannot erode farther downwards than their orbitals reach. So, the shoreline retreats more and more, but the ocean does not get deeper. The water beneath a wave moves in circular orbitals that only reach down half a wavelength and no deeper. Slide 19. If sea level falls, as it does during an ice age, or an earthquake lifts the land upward, then the flat area is no longer underwater and we call it a marine terrace. Slide 20. The process does not stop. Waves start to erode a new wave-cut terrace at the new shoreline, and when sea level changes again, this terrace may get lifted far above the ocean's surface and become a marine terrace. As you can see in the photograph below, Palos Verdes has several marine terraces. People often say that a series of marine terraces resembles the steps of a staircase. Rainwater runoff begins to erode the cliff above the marine terrace, creating a steep slope where the cliff once was. Sediments from the eroded cliff spill out onto the terrace, giving it a small slope and thus making it less flat. Given enough time, the flat marine terrace is buried in sediment. In short, rainwater erosion creates a slope where the cliff and marine terrace used to be. Sea level can go up as well as go down, and often does one and then the other. If sea level goes up, the flat area ends up well below the surface of the ocean, and does not become a marine terrace. Slide 21. Layers in the cliffs. Look closely at our coastal cliffs, where they are not covered up by vegetation or erosion, and you will see that the rock of the cliffs is composed of layers, strata, of rock. This is one indication that the rocks are made of sedimentary rock, sediments which have become stuck together to form solid rock. Slide 22. Sedimentary rock usually forms in valleys on land or on the bottom of the ocean. Sand and mud washed off the land by rain and tiny plankton shells build up on the ocean floor. Different kinds of sediments pile up at different times, resulting in different layers. In other words, sometimes more mud is sinking in a particular spot, resulting in a layer with more mud there. Other times more plankton are sinking at the spot, resulting in a layer with more plankton shells. And other times more sand is sinking, resulting in a layer with more sand. The weight of the sediments building up on top presses down on the sediments below them, forcing out the water between the sediments. Then, the weight of more and more sediments piling up squeezes the sediments on the bottom of the pile together until they stick together, until they are sedimentary rock. Some of the chemicals that were dissolved in the water are left behind and can act as a glue, helping the sediments stick together, as can the warmer temperatures deeper in the earth. The sedimentary rock becomes part of coastal cliffs if an earthquake lifts up the land or sea level sinks. Sea level sinks during an ice age, because more of the water that evaporates from the ocean does not return to the ocean. During ice ages, more water falls as snow and becomes ice on land. Less falls as rain and flows back into the ocean.